So now we're going to talk about mechanical vibrations. And these can occur in any system where I'm going to call it a restoring force. It really could be a couple too, but there's a restoring force that pushes a system back towards equilibrium. And so, you know, some simple examples are the one I'm going to use for the derivation, where you have a cart on a spring, and if you move it and let it go, it'll oscillate back and forth. And do you know actually that these are basically the two ideas that all timekeeping was done with before there were like solid state electronics and whatever. And it's pretty amazing actually how accurate systems can be based on springs and pendulums. So you basically, in both cases, it's a torsional spring that they use, not a linear spring. But in either case, what they do is you have a big source of power, which can be either a mass slowly dropping, or a big thick spring, that torsion spring that's been wound up, and you have this little lever system that just increment by increment allows a little bit of the energy of that power spring to run out of the power spring through this system of gears. And the same thing would apply here. Give this a little nudge, and then it'll say, if you nudge it this way, it'll move back and come forward based on its own frequency. And when it comes back, it moves the hands of the clock or whatever. And same idea with big clocks, So the spring idea was used in pocket and regular watches, wristwatches, and the pendulum system is used in clocks because you can't carry a pendulum around in your pocket.
Why not?
You could. And yeah, you could, if you wanted to be really cool, like, I feel like a big part of what I'm trying to do here is help you be cool when you get to the U, because, or wherever, because like some of those study groups will already be, you got to sort of force your way into the study groups, And so you could calculate the length of the string you need your pendulum to beat, so it ticks exactly 1 second, and then you could just count the seconds to keep time. Just carry this pendulum around. But you wouldn't be able to talk much because you'd be counting a lot of seconds. But yeah, exactly. That would be a very like vaudeville kind of thing. Yeah, exactly. Everybody, no one would be like, it wouldn't be like, hey, that new guy? Like, oh yeah, the guy that's sort of tall but has maybe it's blonde hair, whatever. It wouldn't be like that. It'd be like the guy who carries the pendulum. Like, oh yeah, I know who you mean. Yeah, exactly. I've been at the U. That's how it would go. That's exactly how it would go. Um, we'll do. Actually, I've been at the U more than like anyone else in the history of the U. I took my first class there as a junior in high school and took my last class there when I was 34 or something. They should, but they're too impersonal to notice stuff like that. You know, they still don't know who I am. Yeah, exactly. Oh yeah. Yeah. Um, so we'll discuss just 1 degree of freedom vibrations, and the ideas apply to more degrees of freedom. So 1 degree of freedom. Yeah. Systems. 1 degree of freedom just means that so something has 1 degree of freedom if you could figure out a way to represent its position using a single variable. Okay, whether it's an angle or a linear position, a length from something. But if you can represent the position with one variable, that's a 1 degree of freedom system. And we're going to start with free vibrations. And then forced vibrations. And then damped vibrations. That's not. Yeah, when your dryer starts vibrating, that's what's going on. Damp vibrations.
What about vibrations that happen in electric power? Those are damp vibrations.
That's true. That's true. Yeah. Okay, so let's start with free vibrations, and this is really going to give us the basic differential equation that this is all going to be based on. So the underlying ordinary differential equation, when we add forces to it and damping to it, that's just going to modify this equation, make it more complicated. But say there's a spring connected to the wall and a cart connected to the spring that rolls along the ground. And the cart has a mass m and the spring has a constant k. So what can we say about the resulting oscillations when the cart is moved, somewhere away from equilibrium and released? So that's what we're trying to figure out. Well, a free body diagram of this system would have the weight, mg, and a normal force, n, and then a spring force. And if we say x equals 0, you know, the cart's at x equals 0 when the spring's at its resting length. We have to think about the direction. So we're going to have a magnitude of kx. We know that much about springs. And then we have to think about the sign. Okay, so if this cart has a positive x value, that means from its equilibrium position, we move it this way. Okay, move it, you know, push it this way. What direction is the force going to be that the spring applies to it? The opposite way. So from that, we think that's probably negative. Imagine the other case, move it this way. X is negative, the force is positive. So could have just drawn that as a pushing force with a positive kx, but I usually think of springs as like default tension or whatever, so that's how I do it. And so Newton's second law from this says 0n plus 0 negative mg plus negative kx 0 is equal to the mass times the acceleration, and we know the acceleration is just going to have an x component. We're trying to figure out stuff about the oscillation, which is all happening in the x direction. So we really only care about the x component of this equation. So we get negative kx is equal to ma, or ma plus kx is equal to 0. Bless you. And we're trying to figure out what we want really is we want to come up with a function, not what, want, x as a function of time. Okay. So the acceleration is the second time derivative of the position. So we can write this as, you know, divide both of these. So this is divided by m. The differential equation says x double dot plus k over m x is equal to 0. So this is the main differential equation. We can generalize this. You know, not all systems that oscillate have a spring constant and a mass in them. So we're going to call square root of k over m. You'll see why that is in a minute. Omega sub n, and we're going to call that the natural frequency. It's not actually a frequency, which is a pain when you're trying to keep this stuff straight, but that's what people call it. And then the equation becomes x double dot plus the natural frequency squared times x is equal to 0. I'll call that equation star, and that'll come up a bunch in this. I call this one equation 1. That's the one that's specific to the spring and mass system. And so how do we solve equation 1? let's do it with equation 1. Equation 1 is equation star for this specific. So equation 1 is the more specific case that we're dealing with. Okay, so how do we solve equation 1? Well, one thing about differential equations is the hard part is coming up with the form of the solution. And so a perfectly valid way to solve differential equations, any kind of differential equations, is to just guess what the form is going to be. And if you're lucky and you guess right, you did it. And it's easy to check whether it works, So if I say, let's say x is equal to t squared, then I can take the second derivative of t squared, do this, check. In that case, it wouldn't work. So, we have to keep looking. But all I'm going to say, I'm going to pretend like we just guessed that this form so we're going to guess that x is equal to some constant a times the sign of the quantity square root of k over m times t plus the angle phi. Where a is the amplitude and phi is called the phase angle. One of the problems that I'll give you is just going through this derivation for something other than a spring mass system. So you just need to understand kind of how this works, but you're always going to take the step of just assuming that the form is, in general, this form would be a times the sine of omega sub n times t plus phi. So now that's the solution. We'll talk about how to get these constants in a second. Oh, no, we won't. We'll talk about it next time. But you can use boundary conditions to find phi and a. But what does this tell us about the rate of oscillation? Well, what we want to know is just like how long it takes. It's going to be steady in time. Like an hour later, it would still be oscillating at the same rate as at the start. What does this tell us about the rate of oscillation? We can think of that two ways. They're equivalent information, just expressed differently. The period of the oscillation or the frequency. Well, we know one period, and that's represented by the Greek tau, is when the change in square root of k over mt plus phi is equal to 2 pi. Okay, we don't care what it starts at. We just care that it starts to repeat itself, and we know that with a sine function that happens at 2 pi. And so you can think of that as if you're taking a change and you have all this stuff at instant 2 minus all this stuff at instant 1, and so that c is going to go away. And what we really want is we're trying to find where square root of k over m times tau is equal to 2 pi. So the period of the oscillation is 2 pi times square root of m over k. Okay, that's the period. The frequency, so the period is how many seconds per oscillation. Frequency is how many oscillations per second. So so the frequency f is just equal to 1 over the period. And so the frequency is just equal to 1 over 2 pi times the square root of k over m. So for spring mass, the spring mass system, if you want, so to oscillate faster, period gets smaller and the frequency gets bigger. So if you want the oscillation to go faster, how do you change the mass? Do you increase or decrease the mass? Yeah, so decreasing the mass leads to an increase in the frequency. And then what about the spring constant? Do you increase or decrease the spring constant to speed up the oscillations? Increase K, and that gives you a decreased, no, it gives you an increased frequency. Okay, so if you have a big heavy mass and a flimsy spring, it takes forever for that spring to turn this big mass around. If you have, oh yeah, yeah, that makes sense. And if you have a really stiff spring and you put a tiny little mass on it, it'll oscillate really fast. Now I want to talk about so this is what I want to talk about today. What changes when the spring, the spring mass system is arranged vertically? The answer is not much. I'm going to go through a derivation of that, and I'm going to ask you to go through similar derivations, so you need to sort of follow the steps on this. But the answer is not much. The frequency doesn't change, so the period doesn't change. The only thing that changes is the center point of the oscillation goes from being the resting length of the spring to the spring's length when the thing's hanging in equilibrium. Then I want to talk about when you have springs in series and parallel. How do you deal with those? And I'm going to go through like a derivation of how that works out. Then I want to talk about torsion springs. And pendulums. And those, then we will have covered all the main simple ways that these oscillations go. And then from there, we'll go into combining these different things to different 1 degree of freedom systems of oscillation. Okay, so first, I want to do a derivation of the equation and solution for a spring mass system hanging vertically. So the difference now is that we have to deal with gravity. In the example we did last time, there was a weight force down, a normal force up, but that was out of the totally out of the direction that this oscillation was happening, and so they just sort of disappeared. Now that stuff is going to be involved, and so now we have to make a distinction between the object's location and the spring's resting length and the object's location when the system is in equilibrium. We're going to choose, we're going to set our x equals 0 at the object's location in equilibrium. Okay, so no, equilibrium is if it's just hanging there and you don't have any acceleration, the object's position. And so the springs, what I'm calling the spring's resting length is so this is the length that the spring would have if it was just sitting on a table. You know? And then you hang it from here, put a mass on it, and the mass pulls it down a little bit. You know, and so this is right. So this is the rest length. This is the equilibrium length. And this is what we're going to call, you know, that's like our origin, and our x is going to go towards the ceiling. And so the rest length of the spring, let's see, when the spring is at its rest length, that means it applies zero force to the mass. The object is at location x0. And notice that that x sub 0 is positive. Okay, so what's going on now is that in this system, because the spring and gravity don't interact, when this is at equilibrium, the position it can just sit at, the spring isn't producing any force. When it's hanging, when it's at equilibrium, that spring is producing force. And so the magnitude of the spring force so the magnitude of the spring force isn't kx anymore. What is it? There's a k. Kx minus x naught. Yep. And we have to deal with the signs or whatever. That's not really I don't know. That's not really always a magnitude necessarily, but the absolute value of that is the magnitude, and we have to think about the directions. Well, we're going to think of x as being, so it is a position. So x could be negative down here, positive up there, and then I guess just think of that as absolute value. But we're not technically. We're just using x only. You could use y instead. All of the equations I'm using are in terms of x, so I'm going to keep it that way. All right, so now let's draw a free body diagram. And before we go into the one for the oscillatory motion, let's do a free body diagram and Newton's laws for the thing in equilibrium. So there's the mass. We have the weight acting down. And the force of the spring, I'm going to draw it up, and then if it's, if you have a positive, let's see, so if x minus x sub 0 is positive, the spring's going to be pushing down. So this is going to be negative k times x minus x 0. And we've chosen our x equals 0 to be at the equilibrium position. So this goes away. Okay. And x naught is at the spring's resting length. but we chose x equals 0 to be at the equilibrium length. Okay. Yeah, I know this is, yes. It is awesome because if you don't do it this way, you can't calculate stuff. And so Newton's second law, just in the x direction, says negative, negative. So k x0 minus mg is equal to 0. Yeah. So k x0 is equal to mg. This will come up. Well, this will come up in the rest of our derivation. We're going to use this fact in the next part. So now finally we can do the free body diagram and Newton's second law in a general case. So this is the one that's going to relate to the oscillation. Here, we have the weight acting down. We have the spring force, but x is not necessarily equal to 0. So this is negative k times the quantity x minus x0. Is it clear to everybody what I'm doing with that sign there? So the way I think about these signs is I know that it's going to be plus or minus k times the distance from the current position to the resting length of the spring. And then I just think about if that value here is positive, what's the direction of that force? So if this is bigger than that, we're this way from the resting length of the spring. If we move this way, the spring is going to be pushing down, and that's why I gave it the negative. I don't know. There might be simpler ways to do it, but that's the way I do it. So what it does is it says if this is positive, the spring is going to be pushing down on that. If the spring's pulling up on it like that, this has to be negative, meaning you have to be stretching the spring. Because, if you stretch a spring, it pulls on it. If you compress a spring, it pushes on it. So that's just the way that I think about that. And now Newton's second law. X component only. Says k negative k times the quantity x minus x sub 0 minus mg is equal to ma. And if I move stuff around, I get that ma plus kx minus kx0 is equal to negative mg. So let's make sure all my signs are right on that. So I sort of switched the sides here, but I kept the mg on that side. I moved this stuff over there, and so I think that's right. And now acceleration is x double dot. So we have x double dot plus kx. And then kx0, this is where I'm going to use this fact, what we know about equilibrium. This is equal to negative mg, and all that's equal to negative mg. And so these two things cancel out. And we end up with the equation that says x double dot plus k over mx is equal to 0. Okay. So even though, well, so what's the same and what's different? Obviously, the form is the same. What's different? No, that's the same. That's the same, wherever it is. The only thing that's different is our x equals 0 stands for a different position. So x equals 0 at the hanging equilibrium position. Not at the spring's resting length. Okay, so the oscillations are going to happen around that equilibrium position, not around the resting length of the spring. And you know, I think just intuitively it's a little surprising that it works out the same. I mean, this says that the solution has to be the same. So x as a function of time is equal to a times the sine of the quantity square root of k over m times t plus phi. And all of those mean the same thing they did before. And so the period is equal to 2 pi times square root of m over k. And so the frequency is equal to 1 over 2 pi times square root of k over m. Yeah, well, yeah, there's a few things that are sort of intuitively surprising about this, I think. But why doesn't it? I mean, I guess I don't mean this as like a smart-ass kind of answer, but really the answer is this derivation, you know, like we just went through the physics of it and that's how it works. And I don't really have a better answer than that. I mean, my intuition also sort of says like, well, when the weight pulls it down to that new position, wouldn't that sort of have the effect of making it a stiffer spring or whatever? Like I would think maybe the oscillations would be a little faster or something, but I don't know. It doesn't happen, and that derivation tells us that, you know. So let's do an example. This will also be an example of how to use the boundary conditions to find those constants. So let's say that we have a spring stiffness of 500 newtons per meter. in a mass of 0.2 kilograms. And from the hanging equilibrium position, let's say that we pull the mass 1 centimeter down and release it. And we want to find the differential equation that defines this motion. And we want to find the solution x of t. And then let's say we also want to find the frequency. That's actually probably easier than the other stuff. So the way we're going to do this is draw a free body diagram. We have negative 500 times let's not do all this. Sorry about that. I will have you do a couple of questions where you do derivations of stuff, but let's just go straight to the differential equation. So we know that the differential equation is x double dot plus k over m times x is equal to 0, where x equals 0 is at the equilibrium position. And so we have x double dot plus k over m 500 over 0.02 2500. Right. So 2500 x is equal to 0. And so the general solution is equal to a times the sine of the square root of 2500 times t plus phi. That's not really an explicit solution yet because we don't know what a is and we don't know what phi is. So now we're going to use the boundary conditions to find a and phi. What's the square root of 2500? Ooh. Yeah. A sine quantity 50t plus phi. All right, well, we know that at time equals 0, x is equal to, what's x equal to? If we, yeah, and remember that we're doing this all with positive x going up, and we pulled it down. So x is equal to negative 0.01. And we're releasing it from rest. So also at time equals 0, x dot is equal to 0. So I'm going to use the x dot condition first because the zeros are easiest to deal with. So x dot as a function of time is equal to 50a times the cosine of the quantity 50t plus phi. And so when time is equal to 0, we have 50a times the cosine of phi is equal to 0. So that's our first equation. And then our second equation says, x as a function of time is equal to a times the sine of 50t plus phi. We know that this is equal to negative 0.01 at time 0. So a times the sine of phi is equal to negative 0.01. And there are multiple solutions of this. We don't want that a to be equal to 0, so we're going to look for solutions where, okay, so this is our second equation. We don't want our a to be equal to 0, because that would just give us 0 for the solution. So we're going to say that equation 1 is only going to be satisfied when cosine of phi is equal to 0. And when does that happen? Yeah, pi over 2, negative pi over 2. Let's just use those two. And equation 2 then, I'm going to choose this one so that, because it's going to give us a positive amplitude, but there's no reason to choose one over the other one really. Equation 2 says a times the sine of negative pi over 2 is equal to negative 0.01. So that says negative a is equal to negative 0.01. So a is equal to 0. Yeah, I'm not done writing yet. 0.01.
That's when we lost your exam.
Yeah, exactly. Okay, so what we have is that the solution, x of t, is equal to, yes? Yeah, you could, since A is the first letter in amplitude, I chose the one that I knew was going to give us a positive value of A. But this would be perfectly valid if you did this as, so I'm going to write this as 0.01 times the sine of the quantity square root of k over m times t minus pi over 2. And that's exactly the same function as negative 0.01 times the sine of the quantity square root of k over m times t plus pi over 2. So whichever one of those two you chose, you get one of those two forms.
I'm going to try to pull that on the exam. wasn't done reading.
Okay, and then, so what's the natural frequency? And this is equal to 0.01 times the sine of the quantity 50t minus pi over 2. Or negative 0.01 times the sine of the quantity 50t plus pi over 2. So from this, the natural frequency is equal to 50. And what are the units? We're going to multiply it by, well, we know that what's inside the sine has to be units of radians. We're going to multiply it by seconds. So this is in units of radians per second. Or 1 over seconds. And so the frequency is equal to 1 over 2 pi times the natural frequency, which is 50 over 2 pi. And what's that as a number? What? 25 over pi. 7.958. And that's units of 1 over seconds or hertz. 1 over seconds is equal to hertz.